So this question is a question that appeared on some of your quizzes and also appeared in the course notes. And I'd encourage you to look at this question or questions similar to it, as all of you guys had it on your quiz and it appeared up twice in your course notes, and it's again here on the mock exam. So I'd look at this question and those similar to it. So here, the way that I've been doing it is I've been solving this using the derivative of inverse theorem, which says that f inverse of x, the derivative of this equals 1 over f prime, derivative plugging in the inverse. Okay, so with this, I've been highlighting what is f. Well, f of x here would be secant of x. F inverse of x is arc secant x. F prime of x equals secant x tan of x. So the derivative with respect to x of arc secant x is equal to 1 over, and now I'm plugging in arc secant into secant x tan x. So it's secant arc tan, arc secant of x tan arc secant of x. Okay. And now I want to solve what this is. To do this, I'm going to let theta equal arc secant of x. So x equals secant theta. Okay. Now, with x equaling secant theta, if we try to create our graph for the positive values of x, for x greater than or equal to 0, this is fine. Secant is hypotenuse over adjacent. We get x over 1, and we're fine, and we can complete our triangle, x squared minus 1. However, for the negative case, we have an issue because our hypotenuse isn't going to be positive with x less than 0. Our hypotenuse is not positive, but also our adjacent is supposed to be negative when here it'd be x over 1, which is a positive number. So to fix this, we actually turn secant theta into a piecewise function. Absolute x over 1 if x is greater than or equal to 0, and absolute x over minus 1 if x is less than 0. And this allows us to complete our triangle. Absolute x minus 1 square root x squared minus 1. And while there is a trig formula using sine squared, or using the fact that tan squared x plus 1 equals secant squared, the question that we have when using this formula is, when I take the square root, do I use the plus case or the minus case? And in this instance, we actually use both the plus case and the minus case, but it's hard to figure out which one we use. Whereas I find it much easier to just build the triangle and rely on these triangles to tell us which case it is. So if I look at secant theta tan theta, this is going to equal, and I'm going to break it up into the two cases. It's going to equal absolute x over 1 times root x squared minus 1 over 1 if x is greater than or equal to 0, and absolute x over minus 1 times root x squared minus 1 over minus 1 if x is less than 0. This simplifies to absolute x root x squared minus 1 if x is greater than or equal to 0, and absolute x root x squared minus 1 if x is less than 0. And because these are both the same, it just becomes absolute x root x squared minus 1. And now I can take this expression and substitute it back into my function. So this equals 1 over the absolute x times the square root of x squared minus 1, which is what I wanted in the first place. Now we have this function that says approximate this using a linear approximation. So there's two things we need to create. First, create a linear approximation. Second, plug 8.99 into this linear approximation. And the linear approximation that we're going to use has to be based around a number, and we have to pick a good number. And with the square root function, 9 makes sense because the square root of 9 equals 3. We have to make a reasonable assumption about what point to use, and 9 is a reasonable point to use. So the linear approximation equals f of a plus f prime of a x minus a. So the linear approximation in this example, f of x equals the square root of x. F prime of x equals 1 over 2 root x. A equals 9. So f of a equals the square root of 9 equals 3. And f prime of a equals 1 over 2 root 9, which equals 1 over 6. So my linear approximation becomes 3 plus 1 over 6 times x minus 9. Now that I have my linear approximation, I can plug in my value 8.99. And this equals 3 plus 1/6 times 8.99 minus 9, which equals 3 plus minus 0.01 over 6, which is equal to 3 minus 1 over 600, which equals 1800 over 600 minus 1 over 600, which equals 1799 over 600. And remember, this is a perfectly good number. Yes, it's just less than 3, but this is a really nice way to say that. Next, we're computing the derivative of this function. Now, when we have a piecewise function like this, within a domain, so in the interior of a part of the function, I can compute the derivative by just computing the derivative of this expression. So for x less than 1, f of x equals e to the 2x minus 2 over 2. Thus, f prime of x equals e to the 2x minus 2 times 2, which equals e to the 2x minus 2. Okay. For x greater than 1, f of x equals x squared over 2. Thus, f prime of x equals 2x over 2, which equals x. Okay. So this here is for x less than 1, and this here is for x greater than 1. For x equaling to 1, we have a different story. For x equaling 1, we need to take the limit as h approaches 0 of f of 1 plus h minus f of 1 all over h. And it turns out that because the function breaks apart at 1, I need to break this into two limits. The limit as h approaches 0 from the positive of f of 1 plus h minus f of 1 all over h, and the limit as h approaches 0 from the negative of f of 1 plus h minus f of 1 all over h. Now this limit equals the limit as h approaches 0 from the positive of this 1 plus h goes into this x squared over 2 term. So 1 plus h squared over 2 minus, and f of 1 is 1/2. So it's minus 1/2 all over h. And now I expand to get the limit as h approaches 0 from the positive of 1 over 2 plus h squared over 2 minus 1/2 all over h, which equals the limit as h approaches 0 from the positive of h plus h squared over 2 divided by h, which equals the limit as h approaches 0 from the positive of 1 plus h over 2, which equals 1. So my limit as h approaches 0 from the positive is 1. Here, this is the limit as h approaches 0 from the negative of e to the 2 1 plus h minus 2 all over 2 minus 1 over 2 all over h. And notice that in both cases, the f of 1, this function is equal to 1/2. I have to use this middle function when using the definition of the derivative at 1/2, at 1. Because f of 1 is this function, it's not the top function. This equals the limit as h approaches 0 from the negative. And now I get e to the h over 2 minus 1 over 2 all over h. Or e to the 2h here, e to the 2h over 2. And now this equals the limit as h approaches 0 of e to the 2h minus 1 all over 2h. And this looks a lot like the limit as h approaches 0 of e to the h minus 1 over h, which is our limit that equals 1. In fact, it is because this equals 1 that this expression equals 1. But what we can do now is we can use L'Hopital's rule. We can take the derivative top and bottom, and it gives us the limit as h approaches 0 of 2e to the h over 2, which equals 2 over e to the 0 over 2, which equals 1. We're using L'Hopital's rule. Now, as the limit as h approaches 0 from the positive of f1 plus h minus f of 1 over h equals the limit as h approaches 0 from the negative, f of 1 plus h minus f of 1 over h, f prime of 1, which equals the limit as h approaches 0 of f of 1 plus h minus f of 1 over h equals 1. So now I have the derivative at 1, the derivative for greater than 1, and the derivative for less than 1. and I can combine it into a single piecewise function. My derivative becomes e to the 2x minus 2 when x is less than 1, 1 when x equals 1, and x when x is greater than 1.